Hello everyone, this is Soumya Mandal and today I am going to explain about the DSP Lab Experiment 5, that is the study of first Fourier transform and application on recorded PPG signal. So let's look at it. So the first Fourier transform FFT is an algorithm that computes the discrete Fourier transform DFT of a sequence or its inverse. In the last week's video, we studied about the discrete Fourier transform. So FFT is nothing but an algorithm which computes the DFT and inverse DFT in like less complexity. FFT does the whole work in order of n log n, while DFT does it in order of n square. So FFT can be implemented by two methods, decimation in time and decimation in frequency, though we are not going to talk about it now. So let's look at the lab assignments. The first one was find magnitude spectrum of a signal sampled at 100 Hz using FFT algorithm and compare the magnitude spectrum plot of the FFT with the previous DFT magnitude spectrum plot. So first we included the Arduino FFT library. We are using the Arduino FFT library. It is available in the Arduino library. So you can download it and use it. Then we declared our input array of 75 samples. We have used 25 hertz sampling frequency and 3 seconds of data. Then I declared a double y vector that is like containing 128. Why 128? Because near 2 to the power term after 75 is 128. Because for FFT there is a rule that we need to use 2 to the power n number of samples. So then we declare the object Arduino FFT. FFT is the object equal to Arduino FFT. After creating the object, we have declared two constants. One is samples equals to 128 and another is sampling frequency equal to 25. Next, I have declared another imaginary array, that is V image of samples. Though we are working on the real data here, but we need the imaginary to be 0. Moving average block size equal to 8 and sampling frequency equal to 25. So in the void setup, we are writing serial dot begin equals to 9600. Now, we don't want our code to run every time. So we'll calculate all the things in void setup and print all the things in void loop. Now, after that, we are using moving average on the x of 75 and we are calculating y of I. So once the y of I is calculated, so y is our real data samples and we need the imaginary part to be 0, right? So in the V imaginary of I equal to 0, we will declare for every I equal to 0, I less than samples. Now there are to weight data, we will use FFT.windowing y means our real data, then number of samples, then and the FFT wind time meaning this is that one, and FFT forward means we are calculating forward FFT. We will do also inverse FFT, so we will see at that time. FFT.compute, where we are calculating the first Fourier transform, that is y, comma V imaginary, comma samples and comma FFT forward. So our y is the like y and V imaginary contains the input data, but these will be replaced by the output data. Next, we will compute FFT.complex to magnitude y, comma V imaginary, comma samples, where y will contain the output, that is the square root of square of old previous y and plus square of V imaginary. So this one is done. So we got our FFT. Now if we want to print our FFT, the first 3 lines are there in the void loop, that we are printing the y, because the magnitude should be absolute value and we are calculating the absolute value and storing it in y in FFT.complex to magnitude. So next we need to find the pulse rate. So for finding the pulse rate, the process is same. We will be calculating the frequency maximum, what we did in EFT. So for I equal to 0, I less than samples by 2, we calculated the maximum location And after calculating maximum location, we found the frequency by the formula maximum location into fs divided by samples. After that, samples should be 128 here because it is in frequency domain and we have taken 128 samples, not the input samples. And then pulse rate equal to 60 into frequency. So now we are printing the pulse rate. So let's look at the results. So this is the plot of the FFT, similar to our DFT. If you saw the previous video, you can like compare it. And this is the magnitude spectrum actually of the given PPG data. And the pulse rate what we got is 82.03 with a moving average block size of 8. So this is what we compared our FFT results with our DFT results. Now we are given a signal, PPG signal, which contain respiration signal also, and we need to find the MATLAB code. We need to write the MATLAB code for extraction of respiration signal from the given PPG signal. So this is the MATLAB code. Similarly, FFT and IFFT are valid in MATLAB also. So first, here we are given 25 Hz sampling frequency and 30 seconds of data. Now, the thing is we need to understand that the respiration signal frequency is 0.05 Hz to 0.5 Hz. So we need to extract particularly that range of frequency. So what we did is first CLC clear all and close all for clearing the previous data. Then data equal to load PPG with respect, this is the file name and we are loading the mat file. Then we are storing the whole structure in X, that data.xpg. Now we are transposing the column into a row and then we are finding the size of X. So we got the size in L. Now we are computing FFT underscore com equal to FFT of, we are giving the input array and then the size. Now we plot the amplitude and like magnitude spectrum. We took the absolute value of FFT com, so which will be the frequency spectrum. After that, we need to understand here that the main thing is the 1 to L, like we are making the FFT1 equal to 0 because if you calculate 0.05 into our sampling frequency and all those things, that is total number of samples, like KFSYN is formula is there. So if we calculate with the formula, then we can get the frequency from the index. We need 0.05 Hertz. So that will be around index 2 and the 0.5 Hertz will be around index 16. So we like around 15. So we are taking from 16 to up to the end of samples, like the total size is L. We are making it 0 in the second line FFT and FFT comma of 1 equal to also 0 because we need to keep 2 to 15. So now we are calculating the IFFT in XUP. We are giving the FFT and its size. Then we are calculating the location of the maxima and then we are printing the respiratory rate in breaths per minute. And we also plotted the magnitude and frequency spectrum. That's fine, right? So now this is my input signal where this is the respiration signal mixed PPG signal. Now this is the frequency spectrum of the total signal. Here we will calculate the frequency and keep the 2 to 16 part. We can see. So this is the extracted respiration frequency spectrum. And then we are calculating the inverse FFT. So this is the respiratory signal. And this is my respiratory rate in breaths per minute, which is coming to be 16. So I think you understood, you got this part right. So now we need to do the same implementation in Arduino. So first we included the library, we took 750 samples, then the nearest 2 power n number is 1024. We are declaring the maximum K index and respiration rate. Now we are declaring an object, number of samples, sampling frequency, and we are declaring to array V real, V imaginary, X of FFT is not needed, I forgot to remove. So next void setup, we are writing the code. First serial dot begin 9600, setting the baud rate, and then we are using moving average filter. After moving average filter, we made the V imaginary of I to be 0. Then we are doing FFT dot windowing on the Y is the real part, and samples Y is the moving average real part, and number of samples. Then we are computing the FFT, that is Y comma V imaginary samples FFT forward. But now we'll do complex to magnitude, like we'll find the magnitude spectrum. So the problem is Y will be replaced by the absolute value of Y comma V imaginary. So we stored the Y in the V real of I to so that we can like calculate the inverse FFT later. Now FFT complex to magnitude Y comma V imaginary comma samples. Now what we'll do, we know that we need to preserve 2 to 15 or 1 to 15, whatever it is. If you calculate by copy pen, you will get it. So for k equal to 0, k less than samples, we are iterating a loop, and if it is not k greater than equal to 1 and k less than equal to 15, then we are making the v real of k and v imaginary of k to be 0. Otherwise, we are finding the maximum and k index in the 1 to 15 range. I have written that in one loop only. After that, we are computing the FFT reverse. See the difference here. We are giving V real, V imaginary samples and FFT underscore reverse. Now, here in the time domain, we will get both real and imaginary parts. So, we need to do again complex to magnitude. So, FFT complex to magnitude, V real, comma, V imaginary, comma, samples. That's fine. And we calculated the respiration rate in a similar way, 16 to k index into sampling frequency divided by samples. So we printed this in the void loop. The first thing is for printing the respiration signal, and the second thing is printing the output in breaths per minute. So this is the part of a respiration signal, not the whole respiration signal. This is one part. I will show you the total one in Arduino Live, and we got 16.11. So what is the error rate is around 0.6% between MATLAB and Arduino. That's fine. So let's look at the Arduino implementation. See, this is the respiration signal what we got in a live Arduino. So I am showing you because I cannot took this whole plot in the serial plotter. So you can see this is almost similar kind of thing. So let's go back to the our FFT. So what we concluded is that FFT is fast because you can see in the previous video in DFT we were not able to calculate this much samples. We are only able to calculate around 100 samples of DFT matrix because it is taking some memory. So FFT can do that. Here we took 750 samples and that wasn't a problem. So thank you.